You know that feeling when you walk into a room and it just feels perfect? Not too hot, not too cold, just right. Well, that feeling isn't magic. It's actually this incredible hidden world of engineering. And today, we're going to pull back the curtain on the architecture of air. I bet we've all got that one room, right? The one that's always an oven or an icebox or just feels kind of stuffy. You can crank that thermostat up, down, sideways, but it doesn't do a thing. So, what is really going on? Yeah, the answer isn't that little box on your wall. Nope. The real story is hidden, out of sight. It's in this massive, totally invisible network that's supposed to be bringing you all that nice, conditioned air in the first place. And at the center of it all, you've caught what's basically the building's mechanical heart and lungs. We're talking about something called the Air Handling Unit, or AHU for short. And you know what's crazy? The success of the entire system. For decades to come, it's all decided right here, at the very beginning. First, the foundation. It has to be perfectly level. I mean, if it's off by just a little bit, you're looking at huge drainage and vibration problems down the road. Next up, the gaskets. They have to create this totally airtight seal between each section. And finally, these special spring or rubber pads go in. And the whole point of all this? To make a machine so quiet, you literally forget it's even running. Okay, so the air is perfectly heated or cooled. Awesome. But now, how does it get to you? That's the job of the ductwork. And let me tell you, it's so much more than just a bunch of metal tubes. It's more like an invisible highway, and it's engineered with some math that is probably going to surprise you. This is where things get really cool. See, you can measure a duct in two different ways. There's the physical length, right? What you'd get if you just ran a tape measure from point A to point B. Simple. But then there's the effective length, and that's the distance the air feels like it's traveling. Because every single bend, every little fitting, it creates all this turbulence and friction, making the journey feel way longer for the air. So how much of a difference are we really talking about? Is it a big deal? Get this. A single standard 90-degree turn can add the equivalent of 15 feet of straight duct. Just think about that for a second. One little elbow makes the fan work as hard as if it were pushing that air another 15 feet. Now imagine a whole system with, I don't know, a dozen of those turns. That resistance, man, it adds up so fast. Right, so all this resistance, this friction, in the engineering world, it has a name. It's called static pressure. Basically, it's the force that the fan has to constantly fight against, just to push the air where it needs to go. And if that static pressure gets too high, well, the air just isn't going to make it to those rooms at the far end of the line. And that's when you get those stuffy, uncomfortable spots. All right, so we've figured out how to get the air moving, but we've got another big challenge. We have to make sure that air arrives at exactly the right temperature. And this brings us to a really simple, but honestly a crucial rule of thumb. Don't cool the spiders. To make sure that doesn't happen, engineers have this formula that looks at three key things. First is U. That's just how good your insulation is. Then you've got A, the total surface area of the duct. The bigger the duct, the more area there is to lose heat from. And then there's the big one, delta T, or delta T. That just means the temperature difference between the inside of the duct and the outside. So let's say you've got 55-degree air inside your duct, but it's running through an attic that's a scorching 110 degrees. Your delta T is a whopping 55 degrees. That's a huge difference. And that huge delta T is exactly why this quote hits the nail on the head. I mean, just picture it. You're sending perfectly chilled air through a bare metal duct in that crazy hot attic. By the time that air actually gets to your room, it's barely cool anymore. Like the pros say, you're not cooling the people inside the house, you're just cooling the spiders up in the attic. Okay, so the system is designed, it's installed, the foundation is level, the ducts are all wrapped in insulation, but here's the million-dollar question. How do you know it's actually airtight? Well, it's time for the final exam, or as some people in the business call it, the final boss, the duct pressure test. This whole thing is basically a high-tech hunt for leaks. First, they seal up the entire system. Every single vent and grill gets taped or blocked off. Then, they hook up this special calibrated fan and literally pressurize the whole network of ducts. And finally, a little gadget called a digital manometer gives you the verdict. It measures, with incredible precision, exactly how much air is escaping through all those tiny, invisible cracks and seams. And what you get at the end is just one number. A measurement in CFM, which stands for cubic feet per minute. And this isn't some friendly suggestion either. It's a hard pass or fail test. It's the final grade that tells you if this whole invisible highway for air was built right from the start. So why does that one little number matter so much? Well, because every single one of those cubic feet of air that's leaking out, that's air you paid good money to heat or cool that never even makes it into the room. This quote just says it all, doesn't it? A leaky duct is a leaky wallet. Simple as that. And that brings us all the way back to the beginning. All of this, the intense math, the super precise installation, the tough final exams, it all leads to one thing. This is what the architecture of air is all about. It's a world where the true sound of success is nothing at all. Just silence. Think about it. Every single step we just walked through, from getting that foundation pad perfectly level, to calculating all that crazy effective length, to sealing up the very last seam, it all requires this incredible, deliberate precision. That's the in. And what's the out? What's the payoff for all that painstaking work? It's a system that works so well, so quietly, so effectively, that you forget it's even there. It just becomes invisible comfort. So the next time you walk into a room and it just feels perfect, you'll know. You'll know about the incredible engineering that's hidden just behind the walls and above the ceiling. Which leaves me with just one last question for you to think about. The invisible system all around you, right now, is it a leaky wallet or is it a silent success?